Hey guys, and this session will be on silicon controlled rectifier, and this is also one of the types of thyristor family, and this is mainly used in rectification purpose, and also this is used in the triggering mechanism of the other devices, and that is why it is called the rectifier. The name has been given from the rectification application. And why it is called controlled rectifier is simply there is a terminal which is used to control the rectification size. For example, if I have a waveform and if I want to rectify, then this particular device can be controlled by a control element, and we use this control element as a gate. And when we discuss about silicon controlled rectifier, we will discuss all these things. What is controlled rectifier and what is the control element and all. So silicon controlled rectifier, the name has been given because of the rectification application, and there is a control element used to control the device, SCR. And how this SCR construction will look like. And as I said in the previous lectures, how the current flow happens from one end of the material into other end of the material. That's what we are going to discuss here. So the SCR construction is basically 4 layer like this, and one layer is called P1, the other one is N1, this is P2, and this is N2. And one terminal is taken from this side from P material, the other terminal is taken from the N material. Since it is taken from P, it is called anode, and since it is taken from the N type, it is called cathode K, right? And along with this, we have got another terminal. This is G. It is nothing but gate, and this particular terminal is controlling the current flow inside the silicon controlled rectifier, and we will see that how this will control this rectification. Right. So there are 4 layers, P1, N1, P2, N2. So this is also called 4-layer diode. So the same SCR can be called 4-layer diode. And if you look at this picture closely, we can come to know that there are 2 transistors are involved. If you look at this side, and if you look from here to here, this particular portion acts as a PNP transistor over here, and from here to here, this acts as a NPN transistor. So in the configuration or construction, there are 2 transistors are involved. One is PNP transistor, another one is the NPN transistor. If you divide this construction into 2 halves, one is for PNP half, another one is NPN half, this would be something like this. This is P1, and you may have a structure something like this, N1 and P2, and these 2 are internally actually connected with N1, again P2, and we have got N2, something like this. It means we divided 1 half, P1, N1, P2, this one, and the second half is N1, P2, N2, N1, P2, N2, like this. As usual, terminal is taken here and taken here, and here is this gate. So now this structure is PNP transistor, and this is NPN transistor. And if you want to draw actually in terms of transistors, this can be drawn something like this. With the help of transistor model, we can draw this one something like this. This is your gate, and this is your cathode, and this is your anode. Now see here, this is PNP transistor. So arrow mark is going inside, and this is NPN transistor. So arrow mark is coming outside. And how the current flow happens in PNP transistor and NPN transistor is from, actually this arrow mark says that current is flowing from this side to this side, which means from emitter to collector. Similarly, in the NPN transistor, current is flowing from collector to emitter. And if you look at the overall current flow, this starts from anode terminal and ends with the cathode terminal with the help of the base bias or supply voltage is nothing but the biasing supply voltage in base terminal is gate. Clear? So current flow happens from anode to cathode through two transistors. And this is the transistor model. If simply this can be explained with the help of transistor model. If we apply positive negative, and this is positive negative VAK anode cathode voltage, then this gate will give some current IG, and that IG is nothing but IB current, and this will create VCE drop over here, and this VCE drop will make this junction is positive, and it means the current flow will happen. It is nothing but the IB2, and because of this IB2 and VAK voltage, the current flow happens from emitter to collector. It means this collector current is coming here, and that is applied to the base of the first transistor, which means this is the first transistor and this is second transistor. So this is how the current flow happens. Though we remove the gate terminal after a certain second, this process will continue. Clear? Why? Because we have got a feedback from Q2 transistor's collector to base of the first transistor. So once it is triggered on, right, for some time, then what will happen? This will give feedback to the second transistor, and that will give current to the base. So this process, is regenerative process, will continue. And one can stop this process by removing this VAK. This is one option. Or second option, we can apply negative polarity to the gate terminal. So these are the two ways one can make this particular regenerative operation. It can be stopped with the help of removing VAK or applying the negative polarity. By making VG is equal to 0, SCR will not stop. This will continue to run, right? So either we can apply negative or we can remove this VAK for the current flow. This is a simple transistor model current flow in the silicon controlled rectifier. But to understand the characteristics of silicon controlled rectifier, especially the VA characteristics, we have to analyze more deeper into this construction. So let me take again the same 4-layered PN diode structure for the clear understanding, right? So let us again consider the same PN PN structure. So this is P1, N1, P2 and N2. This is A and this is K and this is G. As of now, we will assume that apply VG is equal to 0, which means gate is open, it is not connected. Now, when we have junction like this, P1, N1, P2, N2 and here N1, P1, the depletion layer will form. It means negative will be forming this side and positive this side for this junction. And similarly for this junction, hole will come this side, it means this is positive and this is negative. And here electrons will move from this side to this side, so hole will be created over here. Clear? Now, if we apply positive, negative VAK like this, then what will happen in the junction? See, according to the junction potential barrier, we can define forward bias or reverse bias. For example, if it is PN, N is coming this side like this and holes are created like this. If we apply the polarity just positive to this side and negative to this side, it means opposite to these two terminals. This is actually nothing but the forward bias, correct? Because plus plus over here and minus minus over here in the material, and forward bias to P type, negative to N type, this is nothing but the forward bias of the PN junction. Here, in terms of potential barrier, this is minus and this is plus, and we apply plus against this minus and minus against this potential barrier plus. So this is nothing but the forward bias. Take this particular concept and apply here. This is plus and this is minus, right? With respect to this polarity, this one is opposite to this one. So what is the junction is either it is forward bias or reverse bias, which means opposite to this one, like this, opposite to this one, this is forward bias. And take this junction, this is plus and this is plus, this is minus and this is minus, it means same polarity. So this is nothing but reverse bias, minus 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 plus plus plus, same polarity means it is reverse bias in terms of junction potential barrier. So this one is reverse bias, and similarly this one is forward bias. This is one case. And if we apply the opposite polarity, you just remember this will be helpful in finding the junction biasing. So second one, if you apply just opposite to this one, so again the same minus 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 plus 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 plus, again this is plus plus minus minus minus, again here minus, and this end is plus. Now see the same, if you apply minus this side plus this side, which means this junction with respect to this minus and this plus, so minus minus same polarity, it is nothing but the, in the PN junction it is reverse biased. Again here minus to this minus, plus to this plus, again this is reverse biased. Now see here, plus to minus, minus to plus, it means opposite potential barrier. So we can say this is forward biased potential junction. Right. Here comes the important point, whether the current will flow or not. If we apply VAK for smaller VAK, if we apply small VAK, let us start from this one. For smaller VAK, which means minus and plus, this junction is reverse bias and this junction is reverse bias, only this junction is forward bias. So for minus VAK, the current will not flow initially, which means because of this reverse bias junction, there will be only a small leakage current, we call that as ICO as of now. Even if you increase this reverse bias voltage VAK with respect to anode and cathode, when we increase VAK voltage, then what will happen in the reverse bias junction? Forward bias is depletion layer sinks. Then the reverse bias, it means the depletion layer width is increasing, and here also the depletion layer width is increasing because the junction is reverse bias with respect to the applied polarity. Then when we increase this VAK to a large amount, then this depletion layer and this depletion layer, they get breakdown. It means for a larger voltage when we apply, these two junctions get breakdown, then only we have a current flow from one terminal to the other terminal. And this is just like the normal PN junction diode, and that's what we say this is reverse biased condition. So this is just like a normal PN junction diode. One can draw the graph is just like this. I'll draw the graph neatly in the VA characteristics point of view. So as of now, assume that initially there is only a small amount of current because of the reverse bias, right? At one particular voltage, these two junctions will break down for a large voltage, and that voltage is even breakdown voltage, right? And this breakdown voltage is high, so V max, and then only we have a current flow. That current flow is also high, so power dissipation that we discussed in the Zener diode is maximum. So if we keep under this condition, our SCR will get spoiled. So this will not actually work over here. This will create more heat, so the diode will get spoiled in the reverse biased junction. So we cannot use this like reverse bias characteristics. When we come to the forward bias characteristics, how this will allow the current is, and you have to be careful in understanding this forward bias sort of thing. See here, this is plus and this is minus. So forward bias, no issues. Okay. So the reverse bias only we have to consider now. When will the reverse bias will get breakdown is for maximum VAK, correct? Just as what we discussed in the reverse bias, we have to apply a larger potential to break this particular reverse bias junction. So large VAK is needed to break this junction so that the current will flow. And this is similar to the reverse bias characteristic because large voltage and large current, that will give you high power dissipation. So when we have high power dissipation, again the SCR will get spoiled. Clear? So here comes the important point, which is nothing but our gate terminal. Now we apply gate VG supply plus with respect to this one. Now what happens in the SCR? So this is plus and we apply to this polarity. Now see here, P2 is nothing but holes, number of holes or height in terms of concentration, and this is negative polarity and this is positive polarity. Now this plus will pushes all the plus in the P2, right? And these plus will not go this way because this plus opposing this plus. Then what will happen? These plus, which means these holes, will move towards the negative polarity. Then what will happen is the junction is again getting increased, which means the reverse bias condition. The depletion layer is increasing because of the holes are depleted, which means deficiency of holes. So this will move to this side. Then automatically the depletion layer is increasing. Initially, we needed large VAK to break this junction, but now we apply extra force from the gate. Then this gate will give extra force to this terminal to break the junction quickly. This has happened in the Zener diode. Do you remember this? Simply, this plus opposes this plus, so all the plus coming this side. So automatically the depletion layer width is increasing. So with the help of this and with the help of this, the reverse breakdown will happen quickly. It means when we have a gate voltage plus a little higher plus, then what will happen is breakdown occurs for small VAK, and this is the very important point one must remember in the SCR operation. It means when we apply a gate, then the reverse breakdown occurs quickly, so we can have the SCR is very safe and we can use this for the operation. But without gate voltage, if we apply large biasing voltage plus minus this side to break this junction, this will damage the diode. So this controlling terminal gate that controls the breaking depletion region. If we apply more and more VG is higher, then what will happen? The more the VG, the quicker the breakdown happens in this particular junction. Right? You got it? So I repeat this operation because it's very important. So initially we discussed about the transistor model, how the current flow happens from anode to cathode. And here, this is forward bias and this is forward bias, so nothing to be worried about because plus minus will break this junction quickly in the forward bias. Only this needed large amount to break this depletion layer because the depletion layer has to be extended to get breakdown. So large VAK again will damage this diode. So we apply some extra force from this side, which means these holes will now quickly come because this hole will pushes the holes. This holes will not go this side because this is plus, this opposes this one. So this comes down, automatically the depletion layer with this increasing. So the more the supply, the quicker the depletion layer breakdown. So one can draw this in terms of VA characteristics. is something like this. In the reverse bias, I will draw both forward as well as the reverse bias junction breakdown in terms of VI characteristics. So this is VAK and this is IF. Let us suppose forward current. Initially, when there is no gate voltage, it requires large amount of VAK current to break the junction. So this is breakdown junction. Let us suppose this is VBR, breakdown junction, right? Once it is breakdown for larger voltage, then the current flow will be higher. But if you measure the voltage across the SCR, once the conduction happens, automatically the voltage across this one is small. Yes or no? If you measure the open circuit terminal, then it will be high voltage. If you measure the short circuit terminal, the current flow will be high, but the voltage is less. The same condition. Once it starts conducting, current flow happens. So this will and this will and this will. All these things act as a closed circuit because current is flowing through this particular junction, 3 junctions. Then we can say that the drop across this, when the conduction happens, is smaller, and that's what the graph shows like this. So immediately the breakdown happens, the voltage is coming down, the current value is increasing with respect to the applied voltage. Okay, and this is for Ig equal to 0 or Vg equal to 0. Let us get now after applying Vg, this gives extra force to the SCR so that the breakdown occurs very quickly. Then this breakdown may happen like this. This is for some Ig1, and if we keep on increasing this current, then what will happen? Breakdown is coming even closer like this. So one can write this is for Ig2, Ig3, and this is Ig4. So to increase this one, breakdown happens quicker so that the diode will be safe and the current flow will be again the maximum current like this. And reverse bias, what we discussed is initially 2 junctions were reverse bias. So to break the 2 junctions, we needed larger voltage, and once we apply larger voltage, then there will be a breakdown happens, and that will spoil the diode actually. And this is reverse breakdown over here. And this is the characteristics of the SCR, right? And this particular time is usually called holding time, because till then no current will flow. So this particular region is holding current. So in many textbooks they have given H1, H2, H3, H4 and so on, right? So usually where we get confused is over here, how when we apply gate voltage the quicker breakdown occurs, so that the quicker breakdown will be there something like this, and how the voltage reduced and the current is increasing like this, right? So this is all about the silicon controlled rectifier. I'll once again recap what we discussed. So silicon controlled rectifier is a 4-layer device, and there are 3 junctions J1, J2, J3. Depends on what polarity VAK we apply to the SCR, the junctions will be in forward bias as well as in reverse bias. So to break the reverse bias, we needed to apply larger voltage in the reverse bias. So the larger voltage and larger current will spoil your diode. And in the forward bias characteristics also the same thing happened. We got one reverse bias junction. To break that one reverse bias junction, we needed larger voltage. Instead of doing that, if we apply extra force to this particular junction, then what will happen? The breakdown occurs quickly, something like this. So the more the gate current, the higher the quicker the breakdown happens. And this is the SCR characteristics, PA characteristics, and how this SCR current flow will control the phase, or how it is used in the rectifier, and that we will discuss in the next lecture. How SCR used as a switch and SCR used as a especially the rectification purpose, how it controls pulses and how it rectifies a particular angle, 180 degree, 90 degree. All these things we will take two examples, like phase control, how this rectifies the phase with the two examples, either 90 degree or 180 degree or some other phases, with the help of SCR, and we will discuss that in the next lecture. Thank you.